Okay, now that we know what geometries need to exist for various types of organic molecules, alkanes, alkenes, alkynes, we have to come to an understanding of how these geometries arise. How do we take the orbitals on carbon, which in its atomic state contains an s orbital and 3 p orbitals as its valence orbitals, and come up with the ability to form molecules with a bond angle of 109.5 degrees. The theory that best explains this is what we call valence bond theory. So valence bond theory is a bonding theory that invokes what are called hybrid orbitals. Okay, hybrid orbitals are sp, sp2, or sp3 orbitals to explain the following two phenomena. First of all, carbon's ability to form 4 bonds in the first place, and you'll see why this is important in a second. And secondly, as I've said, the observed geometries, tetrahedral, trigonal planar, or linear, about a central carbon atom. Okay, so indicated in this picture are the 4 valence orbitals on carbon. So we have the 2s orbital, and you should recall that the meaning of an s orbital is an orbital that is spherically symmetrical with respect to the atomic nucleus. And then there are 3 p orbitals that are mutually perpendicular. For convenience, we define one of them as the py orbital, one of them as the px orbital, and one of them as the pz orbital. In other words, each one points along one of the 3 coordinate axes. So the fact that they are mutually perpendicular means that there is a 90-degree angle between, for example, the px orbital and the py orbital. Okay, so if all we had available to us to use for bonding were the atomic orbitals, the hydrogen-carbon-hydrogen bond angles would have to be 90 degrees, and we know that that's not the case. So therefore, there has to be something more to the theory than just taking atomic orbitals on carbon and overlapping them with atomic orbitals on hydrogen or another carbon atom. Okay, but secondly, the formation of an ordinary covalent bond, the classical general chemistry covalent bond, requires that the 2 atoms coming together have half-filled orbitals. Why is that? A covalent bond means that you are sharing a pair of electrons. One atom contributes an electron, the other atom contributes an electron, they come together, form a bond, and those 2 electrons are shared between the 2 atoms. But in order for that to work, each atom can only be contributing 1 electron, which means it has to have a half-filled orbital. If it has a completely filled orbital with 2 electrons, there's no room to share. There's no place for the hands to shake, for example, on the 2 atoms. Okay, so if we look at the electron configuration, the ground state electron configuration for atomic carbon, it is 1s2, 2s2, 2p2. Well, we're going to ignore the 1s electrons. Those are what we call core electrons, but we're just going to concentrate on the valence electrons, which are the 2s2 and the 2p2. That would give valence orbitals that look like this then. We would say that the 2s would be completely filled, and then of the 2p's, which are higher in energy than the 2s orbitals, we would have an electron in each of 2 of those 2p orbitals, and one of them would be completely empty. Well, what does this mean? We have only 2 half-filled orbitals, so therefore, if this diagram were all we could do, carbon would only be able to form 2 covalent bonds. But we know that carbon forms 4 bonds as being one of the most important principles of organic chemistry. Therefore, there's got to be more to the theory than this picture allows. Okay, so what is hybridization? Well, what we do is we mathematically mix the s orbital with xp orbitals to produce x plus 1 spx hybrid orbitals. And here's the key. that all have the same energy. Okay, so for single bonds, what we want to do is form sp3 orbitals. So in this case, x is equal to 3. So we're going to mix the s orbital with all 3 p orbitals and get 4 sp3 hybrids. Okay, so I have the energies on the left. The s is lower, the atomic orbital energy. The p is higher, and when we mix them together, we get 4 orbitals that are of the same energy in between that of a 2s orbital and that of a 2p orbital. Once we have 4 orbitals that are the same energy and 4 valence electrons, we're going to want to put 1 valence electron into each of those 4 orbitals, and voila, we have 4 half-filled orbitals with the ability to form 4 bonds. Now, the additional advantage here is that the sp3 hybrids point towards the corners of a regular tetrahedron, or at least the larger lobes of it. Okay, so indicated on the right side of your screen is what an sp3 hybrid orbital physically looks like. It has a smaller lobe indicated in blue and a larger lobe indicated in red. When you put together the 4 larger lobes, as I said, they're going to point towards the corners of a tetrahedron. If we want to have a double bond, we will now only want 3 different groups bound to the central carbon atom. So we're going to mix that s orbital with 2 p orbitals to give 3 sp2 hybrid orbitals. Okay, x is equal to 2 in this case. And we're going to leave a p orbital behind that is not part of the hybrid system. Okay, so once again, the s orbital and the 3 p orbitals get converted into 3 sp2s. They have energies in between that of an s and a p, and then 1 p orbital that is unhybridized. Okay, this is a picture of what it looks like. The sp2 orbitals are indicated in gray. The unhybridized p orbital is indicated in red and blue. And as you can see, the 3 sp2 orbitals all lie in a plane, and they have a 120-degree angle between them, and the leftover p orbital is perpendicular to that plane. You should note that the sp2 orbitals and the p orbital are close enough in energy that each one is going to remain half-filled. You're not going to pair up 2 electrons into one of the lower energy, slightly lower energy sp2 orbitals. Because whenever you pair up 2 electrons into one orbital, you pay an energetic price called the pairing energy. The energy difference between the sp2 and the p is less than the pairing energy, therefore we keep all 4 of them unpaired. For a triple bond, carbon, in other words, a carbon that's going to form a triple bond and a single bond, we're going to mix the s orbital with only 1 p orbital to give 2 sp hybrids and leave 2 p orbitals behind. Okay, here's a picture of what that looks like. The 2 sp hybrids lie along an axis, which is the linear axis of a molecule containing a triple bond, and then the 2 unhybridized p orbitals are mutually perpendicular to both each other and to the axis containing the sp hybrids. Okay, similarly to what we did in the case of the sp2, we're going to have 1 electron in each of these 4 orbitals, and once again, the energy difference between the sps and the p orbitals is low enough that all of these electrons are going to remain unpaired. You're not going to want to pay the pairing energy to pair them up. So what we still have the ability to form 4 bonds when we do sp hybridization. In the next lesson, we will go ahead and look at how these hybrid orbitals come together to be able to form carbon-hydrogen and carbon-carbon bonds and thus form molecules.